Hello everybody, welcome back to the Gregorius Maths video. Today is day 2 of the Advent calendar, and in today's video I'm presenting to you some a sum that gives you some really nice, increasingly accurate upper bounds for pi, and this sum actually comes from the more famous Dezell's integral. So if you don't know what that is, I'm sure there's plenty of videos on YouTube about this, which is a proof that 22/7 is bigger than pi. And the way that you do that is you compute the integral from 0 to 1 of x to the 4th times by 1 minus x all to the power of 4 all over 1 plus x squared dx. And the way that you compute this integral typically is you expand this 1 minus x to the power of 4, and when you expand it and you do the polynomial division to get blah blah blah, like a polynomial plus something over 1 over x squared, and then you just compute it normally and you get that this is equal to 22/7 minus pi. And and well, this shows that 22/7 must be bigger than pi because this function here that you're integrating, this is clearly always positive, and so the area under the curve must be positive, thinking of it, an integral's area under the curve, and so we must have that 22/7 minus pi is bigger than 0, and so of course we get 22/7 has to be bigger than pi. So that's Dezell's integral. In today's video, I want to show you an even better version that you can get from this, and it involves this crazy summation, absolutely crazy stuff here going on the channel. So the sum that we're going to be considering today is, okay, I'm just going to keep this on the side. So I'm going to consider the sum from k equals 0 to infinity of 240 all over 4k plus 5 times by 4k plus 6 times by 4k plus 7 times by 4k plus 9 times by 4k plus 10 times by 4k plus 11, like so. So this infinite sum, I claim, right here, is somehow related to this integral, which, maybe sounds crazy, but stick with me here. So now, apparently, if you do the partial fractions, so okay, I'm not going to write out all the partial fractions here because that is insanely long, and I'm not doing that. But it turns out that if you do the partial fractions here, which you can check for yourself if you like, this is equal to the sum from k equals 0 to infinity of, and I have it written down here because I did not memorize this. So we have 1 over 4k plus 5 minus, what's that, 4 over 4k plus 6 plus 5 over 4k plus 7 minus 5 over 4k plus 9, like so, and then plus 4, okay, over 4k plus 10 minus 1 over 4k plus 11. Okay, now, this is fine and dandy, fair enough. It splits up nicely into partial fractions, if you believe me. But like, okay, and basically, this is what you're probably thinking. Well, now, okay, this we want to get an integral involved somehow if we're going to somehow claim that this is related to that. So let's get integrals involved then, I'm not scared to get integrals involved, I don't mind getting my hands a bit dirty every now and then. So notice that x to the 1 over 4k plus 5, that can just be thought of as the integral of x to the power of 4k plus 4 from 0 to 1. Because if you integrate that, you get 1 over 4k plus 5 times by x to the 4k plus 5, and then when you evaluate at 1 and 0, you get this. And similarly for the rest, you will get the integral from, the sum from k equals 0 to 1 of the integral from 0 to 1 of x to the 4k plus 4 minus 4x to the 4k plus 5 plus 5x to the 4k plus 6 minus 5x to the 4k plus 8 plus 4x to the 4k plus 9 minus x to the 4k plus 10 dx. So, okay, the first thing we can do, and again, nicely relating here, we can sort of see what's going on, maybe, is we can take out this factor of x to the fourth. Sorry, what am I saying? Oh yeah, we can move the sum and the integral. We're just going to assume that we can do that. And then we can take out the factor of x to the fourth from the sum, because it's got no dependence on k. So we get the integral from 0 to 1. Sorry, I should write this more nicely. We get, okay, let's just swap the sum and the integral, you know. I am a pure guy, but I'm not that pure. I'll just swap it. Of x to the fourth, so we're taking out x to the fourth, and then we do the sum from k equals 0 to infinity of, what do we have left? Or we have x to the 4k minus 4x to the 4k plus 1 plus 5x to the 4k plus 2 minus 5x to the 4k plus 4 plus 4x to the 4k plus 5 minus x to the 4k plus 6 dx. Okay, good. Now, this sum here, so this is equal to the integral from 0 to 1 of x to the fourth times by, well, what does this sum evaluate to? Well, again, the only thing that really depends on on k here is the factor of x to the 4k. So we take this factor of x to the 4k, and then the rest of it we can take outside of the sum. So we just have that this is the sum from k equals 0 to infinity of x to the 4k, and then multiplied by 1 minus 4x plus 5x squared and so on. And the sum from k equals 0 to infinity of x to the 4k, well, that's just a geometric series. First term is 1 because we start k equals 0, and the common ratio is x to the 4. So we just get 1 over 1 minus x to the 4. And so overall, this sum gives us 1 minus 4x plus 5x squared minus 5x to the 4 plus 4x to the 5th minus x to the 6th all over 1 minus x squared times by what, sorry, what am I doing? I've skipped a step. Over 1 minus x to the 1 minus x to the 4, like so, dx. Okay. And okay, now what we want is to get this 1 plus x squared term. So this is equal to the integral from 0 to 1 of x to the 4th times by blah 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 all over 1 minus x squared 1 plus x squared dx. And well, okay, it turns out that if you divide this thing by 1 minus x squared, you get 1 minus x all to the power of 4. Which again, I'll leave to you to check because that's slightly long and tedious and not entertaining for the viewer. And of course, if it is entertaining for the viewer, then feel free to pause the video and do that yourself. But yes, it does turn out that we can just cancel that, and we get the integral from 0 to 1 of x to the fourth times by 1 minus x all to the power 4 times by 1 plus x squared dx, like so. And that's equal to 22 over 7 minus pi. Okay, so what do we see? So, okay, in conclusion, if this green pen has any life, I'll write the conclusion over here. In conclusion, we have that this sum is equal to that. So we have that the sum from k equals 0 to infinity of 240 over 4k plus 5, 4k plus 6, 4k plus 7, 4k plus 9, 4k plus 10, 4k plus 11 is equal to 22 over 7 minus pi. And if we want to write this in, I don't know, a slightly cleaner form, you know, so that we're not starting at 5, if we just shift the index so that we start at k equals 1, and then we just replace all of these k's with k minus 1, then we can just see that this is the sum from k equals 1 to infinity of 240 all over 4k plus 1, 4k plus 2, 4k plus 3, 4k plus 5, 4k plus 6, 4k plus 7, yeah. Like so. Okay, that says 4k plus 7. And so, what else do we notice here? Why do I say we get infinitely many upper bounds? Well, okay, this starting at k equals 1 gives us 22 over 7. If we started at k equals 0, we would get 10 over 3. But that's even worse bound, so okay. But obviously, all of these terms are rational. So if we keep truncating, so for example, if we did the sum from k equals 2 to infinity, well, that would be 22 over 7 minus pi, but you have to take away the term at k equals 1. So you take away 240 over 5 times 6 times 7 times 9 times 10 times 11, you know? So if you start at k equals 2, you get an even better bound, because you're just taking away rational terms. So you're just taking away from this 22 over 7, basically, to keep on getting better and better upper bounds for pi. And the reason I say upper bound is because, well, this is clearly always positive. So we get some rational number minus pi, and yeah, so this sum, if you do the sum, in conclusion, if you do the sum from k equals n to infinity of this thing, 240 over blah, 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 gives upper bound for pi, and as you take n to infinity, bound is more accurate. Because this gives you an upper bound for pi, and as you take away more terms, you're shaving off a little bit from the upper bound. And yeah, I think that's I don't know, personally, I think that's a really cool result. And also note that this sum from k equals n to infinity, well, what does this correspond to? Well, at this step, if instead of taking out x to the power of 4, you took out, oh, where am I going with this? Yeah, maybe I'm, hold on, where am I going with this? Yeah. Oh, no, sorry, yeah, if you took out x to the 4n, then in here you would get the sum from k equals 0 to infinity of x to the 4k minus, sorry, 4k minus n. Instead, wherever you see 4k, just write 4 times k minus n if you took out 4n instead. And so that would be the same as starting the sum from k equals n. Oh, sorry, it would be 4 k minus n plus 1, right? So then you'd be starting this sum at n minus 1. So then you would be starting this sum at n. And so this truncated sum corresponds precisely to this generalized what's his name? Delzel's integral, where instead of just doing x to the 4, you do the integral from 0 to 1 of x to the 4n times by 1 minus x to the all to the power of 4 over 1 plus x squared dx. So yeah, this sum, viewing this integral in sort of summation terms gives us really nice, easy upper bounds for pi. And also it just looks kind of crazy, this sum. Yeah, and the more terms you shave off, as I say, the better your approximation. So you could basically just take this sum, plug it into a computer, and just do 22 over 7 minus this amount of terms. Now, bang, you got a better approximation. So yeah, I thought that was a nice video. Hopefully you enjoyed that, and I'll see you tomorrow. Ta.